those of you at home, you'll need a periodic table essentially and a polyatomic list for this lecture. Also, pause, copy that. All right, we're going to do two little acid-base things today, but they really rhyme with stuff we've done before. The first thing is new, but it could have been taught earlier, and the other thing is not new. We're just revisiting something I previously taught you because it fits super good here to review it. But I'd like to take you back to February real quick when we did a unit called reactions, and back when we were doing that, you got very good at differentiating between synthesis, decomposition, redox, and precipitation. And we just left it at that. Well, there are more types of reactions than those four. One of them is neutralization. A neutralization reaction is when an acid reacts with a base. The reason that we don't teach it then is because we haven't given you any acid-base background at that time. So it's kind of a gray area for us. But now that we are fully fledged with acids and bases, you've even made a beautiful Venn diagram because you're so smart, we can introduce you to a new type of reaction that was skipped back then. One of the things you were really good at during the reactions, or that you should have been, was identifying which type you were looking at, so then you knew what to do. For example, if you identified a type as precipitation, double replacement, you would say, okay, well, that's a compound reacting with a compound, which means after I predict the products, I need to label solubilities with S's and AQs. Does that ring bells? Y'all remember all those things? So if we would have done the same thing with this new one, neutralization, then we would have said it's an acid reacting with a base, and it always produces salt and water. Now, the word salt, we've used it before. I want to remind you that by definition, salt is any ionic compound, a metal bonding with a nonmetal, or a polyatomic bonding with anything. Water is always water, H2O, so it's always going to form H2O when an acid and a base react together. But there's thousands of salts, so which salt is going to form? Let's figure this out. All right, y'all, we're going to do 4 of these reactions today. Please copy down the reactants of the first one. I'll write them for you. Here we go. I know it's neutralization because it's an acid. See the acid? Starts with H. Reacting with how do I know that's a base? Hydroxide, very good. We learned on Wednesday that the OH is indicative of a base. So, acid reacting with base. Neutralization. We know it's going to form salt and water, but here's how you do it. This is essentially a double replacement reaction like you'd previously studied a compound reacting with a compound. And we're going to do what we did then, where you take the very first part of both compounds and you just switch their positions. All right. So in other words, the first part of the acid is hydrogen, of course. The first part of the base is lithium in this case. I'm going to switch their positions. Now, the red arrow, you don't have to draw that. That's not chemistry. That's just me teaching. I hope you can see this movement without drawing the arrows. But anyway, on the product side, the PO4 phosphate, if you look it up on your polyatomic list, isn't going to move. Instead, this lithium here is going to move right to where my hand is, and it'll be LiPO4. The hydroxide is not going to move. Instead, hydrogen's going to come right where my hand is, and it'll be HOH. However, I would rather you not write HOH. It's technically not wrong, but it makes you look like a little baby chemistry student. What should you write instead of HOH? Yeah, H. Because we knew water would form. Now, that is the products. However, you must check the salt. That ionic compound requires a nomenclature check. So let's click back into how we think about that, where we see that lithium. Here, flip your packet to the very back. The very back. See that periodic table? Santa up in here. If you verify lithium's position, you'll see that he is +1. What is phosphate? Look on your polyatomic. -3. All right. So following your ionic rules, the numbers are not divisible by each other. So the 1 crosses to phosphate and does nothing. The 3 will show up right here. And boom, we have analyzed a neutralization reaction. Let's do another one. We'll draw some cards this time. Let's go talk to someone. Let's go over to cluster 2. Ooh, a full cluster. The only full cluster in the room. Oh, no, cluster 2, seat 6. Hey, 2-6. This is a neutralization reaction. How do I know? Perfect. It's an acid and a base. Acid starts with H. Base contains OH. Boom. Neutralization. So our products are automatically very generally predictable, right? Let's go talk to someone else. Let's go to cluster 6, a highly empty cluster. Seat 5. Hey, Aspen. Can you name what one of the products will definitely be? Say again. All right. All right, these are our constant products. So one of them is definitely H2O. But we can prove it as well. So instead of just writing the H2O, let's look at our ion swap. The first item in the FeOH2 is the iron. The first item in the HBr is the H. So these dudes will be the ones that switch. The OH is going nowhere, but the H will be right here for HOH. And if you're sitting there and you're thinking, but sir, what about the little 2? Why aren't you bringing him over? We've been tested on this. We know that the only subscripts that get to automatically move over are polyatomic subscripts. All right, subscripts that live on this sheet and that are always there. All right, like phosphate. See the PO4 from our earlier example? That 4 is on the polyatomic list, which is why it automatically moves over. But that 2, there's no OH2 on the list. The only reason it's got that 2 is because iron is creating it. But we're not staying bonded to that. Instead, HOH rather H2O. The other product. The bromine's not going anywhere, but the iron is going to live where my hand is for FeBr. But check the charges of the salt. You must do that for the ionic compound. Hey, this one's a little trickier though. What is iron's charge here? It is, remember, usually Roman numerals are given to us for transition metals, but that wasn't the type of data we were given. But you could reverse engineer it. The iron over here crossed a 2 because his charge is 2. Sorry, I keep checking my phone. My daughter, my youngest, broke her foot, so I'm getting updates. She's fine. It's just a broken foot, but it still sucks. And now it's forever. So now you people at home know. But my daughter broke her foot. Anyway, yeah. So it's +2. If you look at bromine on the periodic table, it's in the -1 group. So there will be a crisscross there. Questions? How we feeling? Smart on a Friday? Do one without me? Yeah. Hey, how about this? Let's do 2 without me. Here's what's about to happen. I'm gonna put 2 more problems up here and give you a couple minutes. The first one is gonna look just like these. I mean, it's different stuff, but same thing. Do it again. The other one's a bit more fun. When you see the other one, you're gonna go, what? But here's the trick. It's neutralization. All right. There's actually lots of answers it could be, but as long as I tell you that the weird one at the bottom is neutralization, there's only one right answer. See if you can outsmart it. But start with the easier of the 2. Take a couple minutes, communicate with each other if you need to. People at home, pause for a moment. The bottom 2. Let's see how you did. The first one is carbonic acid reacting with calcium hydroxide. Acid with base, H with OH. So I'm going to switch the H and the Ca. All right, so if the calcium comes over here and takes that spot, it'll become CaCO3. If the hydrogen comes over here and takes this spot, it'll become HOH. We know that we have to check our charges of the salt that we make. Calcium is +2 from group 2. Carbonate is what? -2 on your polyatomic, so there is no crisscross. By the way, we could be balancing these as well. Most of these are unbalanced. You could add coefficients after you're done with all of the translating and predicting, but you're good at that. How'd you do on the second one? Again, with those question marks, you could put a bunch of different stuff in there, but if it's neutralization, the predictability becomes a lot more evident, because what must the other product be? It's got to be water. And now that you know both products, all you have to do is unswap the first parts, or reswap them, however you look at it, and you can get those answers. So over here, the H was in Na spot, so it would be the H with that dichromate. So HCr2O7. But you do have to check the charges of acid. So I hope you went and verified that the hydrogen is +1, the dichromate polyatomic is -2, so they will cross. Well, what about the other reactant? All right, well, that would be sodium going to that location, so NaO, but you didn't write NaO because you're too smart. You wrote NaOH because it's neutralization, and we need that dude to be a base. No, we're not done. There's other stuff in the dark. Quit putting your stuff away. Stupid kids. Besides neutralization, the other thing I'd like to review with you is acidic nomenclature. We did exactly this back in November, but at that time, it was with ionic and covalent nomenclature, and then we had units that really dove deep into ionics and covalents. And we didn't talk about acids. Since we are now, acidic nomenclature is really important. So let's work back through quickly a handful of problems and remember how this works. Now, you'll need your acid rules in front of you, which are right here, but you wrote them already in the dark. So let's just remember how this works. Write down our first example. There he is. Let me walk you back through one of these. I want to know the name of this acid. Well, I know it's an acid because it starts with H. And once you know it's an acid and you know these rules are going to activate, you don't worry about the H anymore. You worry about everything else. And you're asking yourself, how do I pronounce a bonded sulfur? Well, that element lives by himself in this area of the table, and you should remember that the non-metals over there, when bonded, have an "ide" put on the end of them. So in other words, a bonded sulfur is really pronounced sulfide, which will activate this acid rule because of the "ide." However, I don't want the "ide." once I know the rule, I want everything that is not the ide to go into the associated blank. Therefore, hydro blank ic should be hydro, then take that sol, and hydrosulfic is fine. I'll never count that wrong. English is weird sometimes. It's hydrosulfuric acid. But again, if you put hydrosulfic because you're literal, you're cool with me. Yeah? Let's see if we remember how to go the other direction. Nitrous acid. When you see the word acid, the element that runs through your brain right away is hydrogen. So I know it starts with hydrogen. The question is, what else is there? And that's where we want to investigate the word nitrous. And if you compare nitrous to your rules, you'll see that it obviously is ending in us. And before it ended in us, it wasn't nitrous, it was nitrite. Go look up nitrite on your polyatomic list. What do you find? NO2. There he is. NO2. Now, remember, you do have to check nomenclature charges of acid. So, HNO2 is the answer, but if you verify and look them up, you'll see that he's +1, -1, so there is no crisscross. This is ringing bells, yeah? You do a couple. Let's find out. There's a card draw in your future. Do well. Talk to each other if you need to. Translate both of those. If you're worried about being called on, listen to me for a second for the first example. Here we go. H3PO4. All right. I know it's an acid because it starts with H. Now you're focused on how to pronounce PO4. Just go find out how to pronounce them. Activate one of those rules. Let's go talk to cluster 1, seat 1. Hey, Aspen. Jacob. Hey. Have a guess on the name? Yeah. Yeah, that's the name of the partner. All right, I'll check it out. So PO4. PO4. All right, so apply it. So what will it turn into? Apply it to those rules. Instead of phosphate, it'll be phos. Look at the bottom. 8 over to ic. Now, if you put phosphic again, that's totally cool. It's really phosphoric, English-wise, but whatever. Questions there? What about the last one? Thiosulfuric acid. Any guesses? Anybody want to just throw out an answer? Ooh, it's perfect. H2S2O3, because thiosulfuric doesn't start with hydro, but it does end in ic. So it's down here still. So before it was thiosulfuric, it was thiosulfate, which is S2O3 minus with a charge of -2. So S2O3 with a charge of -2.